Okay, so today we give two lectures. One will be some kind of recollections about Sullivan's rational homotopy theory of spaces. And in the second part, I will explain how to upgrade this theory from spaces to operads. Okay, so I need a careful survey in order to see which problem we will face later on when we will try to extend this theory. Okay, so the goal of the first part, goal one, is to explain the definition of a topological counterpart of the rationalization functor on modules. So this means I would like to get a functor x maps to x hat on spaces such that the fundamental group of x is the Maltsev completion of x hat is the Maltsev completion of a fundamental group of x. And the higher homotopy groups of x hat are just the usual rationalization of abelian groups. I mean, you take the tensor product with Q over Z. This is for degree larger than 0. Okay. And so this should work. So actually I'm not giving a functor which works in every case. This should work at least for x good enough. Means, for instance, nilpotent nilpotent, but the example which I'm going to consider so I should say the first example considered by Sullivan is the case of surfaces which are not nilpotent spaces at all. And similarly, I would like to consider surface of a genus G. In that case, the nilpotent condition fails, but it still works, it still gives interesting results. And the example which I would like to consider is the classifying space of a purebred group. So this is the purebred groups on R strands. So I'd like to explain that this construction fits this framework, and in that case I get the classifying space of a Maltsev completion of R, of course, because of S conditions. Okay. And the second goal is to explain how to compute, how to use a Sullivan model, an algebraic model, for the computation of homotopy classes of maps from X to such a completion. Okay, so this is for homotopy classes of maps towards such a rational space. And so it's something which I should also denote by the morphisms in the homotopy category of topological spaces of maps from X to Y hat, where Y hat is this rationalization of Y. And the byproduct is the existence of this model, the Sullivan model, gives some kind of qualitative results on homotopy automorphisms groups of spaces. So it's our structure. Results on H hot x hat. So I will consider the automorphisms of rationals of the automorphism of space x hat of the rationalization of a space in the homotopicity of topological spaces. So the structural result said that mainly this group of homotopy classes of self-homotopy equivalences differ from the automorphism of the cohomology by a unipotent group. So that's the point which I would like to explain at the end. Okay. So okay, first 3 parts. So first I'm going to explain the definition of a Sullivan model, the definition of DG algebra of PL form. So PL stands for piecewise linear or for polynomials. So this is the algebraic object which captures this rational homotopy information on spaces. In the second part, I'm going to explain how to use the models in order to do computations, homotopy computations. And in the first part, I will address this subject, so the applications of minimal models to the study of homotopy automorphism spaces. Okay, so everything should be classical. So first part. So the idea is to define a functor. So I should say a version of the cochain DG algebra of differential forms, of Durham forms, satisfying 2 features. So I will denote this cochain DG algebra by APL of X. So first point, APL is defined for all topological spaces. Or rather simplicial sets. So not only manifolds. And second point, this DG algebra is defined over Q. Okay, so it's a kind of rationalization of the Durham cochain DG algebra. Okay, so to define this algebra, so one has to deal with simplicial sets. So the construction is performed in 2 steps. First, one defines this algebra of piecewise linear forms for the simplices. And in the second step, one uses some kind of N construction. So categorically, it's an N construction to extend APL to all simplicial sets. So the main ingredient is this object. So I need to maybe to recall some conventions. So delta n top stands for the topological organization of the n simplex. So it's a set of points in Rn, or I will use denote these coordinates by x1, xn, such that 0 is less than x1, less than x2, less or equal than xn, and xn is less or equal to 1. Okay. And so you have so it's a co-simplisher object in the category of topological spaces. So this means we have coface operators. Di going from delta n minus 1 to delta n. So these are defined for I equals 0 to n by the following formulas. So we have three cases. So di of x1, xn. So in the case where I is 0, then you just insert a 0. For I equals to 1 from 1 to n minus 1, you just repeat the ith component. Oops. It's an element. And for I equals n, you just take 1 as the last component. So maybe I should draw a picture. So delta 1, this interval. So you have one vertex which is numbered by 0, which is here, another one which is numbered by 1, which is here. And delta 0 is just a point. And the map d0 corresponds to this embedding of a point in delta 1. And d1 embeds this point at the other extremity. Okay. Delta 2, you get this picture. So it's a set of x1, x2 such that x1 is less or equal than x2. So I think it's oriented like that. So you have this is the 0 vertex, this one is the first vertex, and this one is the second vertex. And this d0 embeds, identify delta 1 with this boundary, d1 with this boundary, and d2 identifies delta 1 with this space. Okay. So you have also together with the coface operators, you have the codegeneracy maps. Given by Sj, which goes from delta n plus 1 top to delta n top. And so these are defined for j equals 0 up to n. And these are defined by Sj of x1, xn plus 1. You just remove the jth component, the j plus 1th component. Okay. So geometrically, for instance, in delta 2, I think that so Sj corresponds to S1 corresponds to this projection, and S0 to this projection. Okay. So to define the algebra of polynomial forms or the algebra of piecewise linear forms of delta n, this is just Q of x1, the polynomial algebra generated by the variables x1, xn in degree 0, and dx1, dxn in degree 1. So polynomial means with the usual graded commutation rules. And this algebra is equal with the differential such that, so it's a derivation, the usual Durham derivation. So it's the usual Durham derivation of polynomials. So this object forms the collection of this object, forms a simplicial object.
Delta n to delta n. I think the plus one is
So in this object forms a simplicial object in the category of cochain graded, cochain DG algebras, commutative, unitary commutative, cochain graded, DG algebras. So simplicial objects mean that the coface operators and the codegeneracy operators induce dual operations on the collection of SDG algebras. Okay? So it's functorial with respect to n. So to get something which, to get a good object, then to get a good extension of this object to simplicial set, you need two features. So this is a proposition. First is called the acyclicity condition. It says that the cohomology of this algebra is k in degree 0 and 0 otherwise. For every dimension, for every simplicial dimension n. And the second condition is the extension property, the extension condition. It says that if you fix, now you fix the degree, you fix the degree of the forms, and you consider this object. So you fix the degree in the cochain algebra, but you make the dimension of the simplices vary. Then you get a simplicial object in the category of Q modules, or K is Q. And you can so it's a simplicial Q module. And you can compute the homotopy of this simplicial Q module. So it's easy to compute the homotopy of a simplicial module, just the homology of an associated normalized complex. And the claim is that this object is 0 in all degree, and for every simplicial dimension. For every degree d, and here the star is the degree which comes from the simplicial dimension. Okay, so this extension condition follows from some kind of polynomial version of a Poincaré or Betti lemma. Maybe Betti for Italian, Poincaré for French. So So once you have this object, it's very, so the definition of a DG algebra of piecewise inner forms to all simplicial sets is straightforward actually. So what you take, so formally, so in the categorical formalism, it's just a coend, it's just an end. So X is any simplicial set. Okay. So it's defined for K, a simplicial set. Okay, so a collection of simplices with face and degeneracy operators. For instance, K is the singular complex of any topological space X. So a set of maps, of continuous maps from delta dot to X. So to define the DG algebra of piecewise inner forms on K, what you take is the end of a ket of delta of morphisms in sets, so maps, just maps, from K dot to a PL of delta dot. So maybe I can expand this definition. So this means that an element alpha in the cochain of degree D in a PL D is a map alpha which to every simplex of dimension n in K associates a form alpha of sigma in A, PL, D, the polynomial forms on the n simplex, delta n. So intuitively, these forms, so it's some kind of form defined on the simplicial set K, and intuitively the image of this simplex sigma represents the pullback of the form alpha to the simplex delta n indexed by sigma. Okay, so K is a collection of simplices, sigma, and alpha of sigma is just the pullback of a form, which is morally defined on K, to the simplex sigma. Okay. And so, and you need the condition that sigma intertwines the alpha intertwines faces on degeneracy operators. So the image of the face of sigma corresponds to the action of the face operators on this simplicial DG algebra, and similarly for degeneracies. Okay. And so the statement that this works.
Sorry, you said that this integral over delta means you take the things which intertwine face and degeneracy.
Yeah, yeah.
Okay.
So that's the meaning of the end construction, exactly. So basically it just passes. So the firm is that this works. So first, before to explain that this works, I should say that you have an integration map. So you should say an integration pairing, denoted by I. So you start with such a form on K, and an element in the normalized complex of K. So it's so the complex of simplices modulo degeneracies. And to this pair, you can associate a number in Q. This is just the integration over delta n of the pullback of the form alpha to the simplex indexed by sigma. Okay, so this is a pairing. So this pairing is preserves differentials, and the theorem is that this map, the dual map, the adjoint map, the weak equivalence of DG modules from this Scott-chain DG algebra to n upper star, so the DG algebra of maps from n lower star k to q. Okay, so this pairing is perfect. So weak equivalence means induces an ISO in homology. DG modules are by definitions the morphisms of DG modules which induce an ISO in homology, in cohomology. Okay. And actually, to get this statement, you just need this theorem actually is a consequence of the acyclicity and the extension property. I mean, each time you have a simplicial DG algebra which fulfills the acyclicity and the extension property, if you apply this construction to extend the algebra to all simplicial sets, then you have such a statement. Okay. And the corollary, that the cohomology of this algebra is the cohomology of a simplicial set K. So you really get a version of the Durham DG algebra which lands in the category of DGQ algebras, which is defined over Q. Okay. Second statement, and if you take the extension of this DG algebra to the realms, I mean, if you take M, so if you take the singular complex of a manifold, say, you take the extension to R, okay, so for M a manifold, smooth manifold. Then you get the DG algebra defined over R now, which is weakly equivalent as a DG algebra to the DG algebra of the round forms on M. Okay. So this means weakly equivalent as a as a commutative DG algebra. So you get something which is really a rational version of the Durham DG algebra. Okay. So we can try to look at properties which we will need for the extension to operads. So for the extension to operads, we need some symmetric monodal structure. We need some QNF isomorphisms. And then we face a problem. So actually, you have the following statement, theorem. So we have a QNF morphism going from A upper star PLK tensor A upper star PLL, and it goes to A upper star K cross L. And this map is a quasi-ISO, it's a weak equivalence of DG algebras so which is a weak occurrence, so which induces an iso in cohomology. So you can see that it relies the classical QNF isomorphism in cohomology at the level of this Grothendieck-Teichmüller. Okay, so it's a weak occurrence, and hence this morphism is a weak occurrence of DG algebras. So just this map is just induced by the product of forms. So
you've also, I suppose, natural in K and L.
It's K, natural in K and L. So just the product.
So it's some bisimplicial map,
yeah, but it's just the product. Okay, so it's very simple. So you take a form on K, you pull back this form to K cross L. You take a form on L, you pull back this form, and you take the product. And this gives a weak occurrence.
So maybe you should do the case of K and L, the one simplex, just so people understand that it's a tiny bit subtle.
Yeah, in fact, what you can check, so yeah, the best is to look at this integration map, okay? And then what you can check is that it corresponds to the Hilbert decomposition
so my
of
point
delta
is
1.
that the left guy is tiny compared with the right.
Yeah, exactly.
Yeah.
It's smaller, it's much smaller. Okay? And so you see the point, so it's exactly what Ezra said. So weak occurrence and not an ISO at the code chain level. So this means that if you want to consider an extension of this object to a product, then you face difficulties. I mean, you start, if you take P, so the underlying connection of an operads in simplicial sets. In topological spaces, that's the same. So what do you have? So we have we would like to equip this collection. We would like to equip this collection with maps reflecting the composition structure of the opera. Okay? So we start with A PM, tensor A of Pn. So we have this QNF quasi-ISO going that way. And the map induced by the composition product of our part. So because it's contravariant, so it goes that way. So you see, we don't get any co-multiplicative structure. We have to get a co-multiplicative structure on this collection. We would have to lift this map to this left-hand side. And I don't know how to do that. So, we need more. We need some kind of lifting which is coherent with respect to associativity relation and so on. Which is so. Then there is a problem. Okay. So maybe I will fix this problem in the second part. Okay. Yeah, maybe. So in any case, with this functor, you cannot do that. So you can forget what I said at the beginning of this talk. Okay. So, but anyway, so how to fix that? So you will see. Okay. So now what I would like to do.
So if I can make a tiny remark.
Yeah.
That this is so different from then the Allenberg-Zilber theorem, where they have an explicit map back in the other direction.
Yeah, exactly.
Which is even an isomorphism.
So in that case, you have an explicit map. I think you can integrate, if you take K cross L to be a Cartesian product of simplices, I think you can integrate on this. So if you take delta M cross delta N, you can go back, if you can forget this part. You have a retraction of so you have a map that way. And this map has a retraction, which is just the integration of over
so
N.
You can define
so you have something like that, so at least.
You'd expect the front face, back face, Alexander Whitney in there, wouldn't you?
Yes. So
This map is symmetric.
yeah, this map is symmetric.
You, in some sense, does that.
The map going backwards, some kind of Alexander Whitney map.
I think this one is the Alexander Whitney map.
This one is.
This one,
This one is. Yeah.
Yeah.
The other one.
Oh,
is
yeah.
So it's quite different from
Sorry,
shuffle.
sorry. This is the cut product, isn't
Yeah,
it?
exactly.
Yeah.
Because the left-hand
But
side,
it's totally
yeah.
commutative, right?
Yeah.
the right-hand side is a direct sum over shuffles.
Yeah.
Yeah.
Yeah, if you look at the integration, then you get exactly the Erlenmeyer-MacLane map. I mean, okay.
Oh, that's cool.
So,
I mean, in topology problem is that the one map, I forgot what, is symmetric and another one is not symmetric.
yeah, so like this one is, yeah, also, yeah. So you have problems in any case.
You have the same
So
problem.
you can also try to fix things by considering cosimplicial objects. Okay. So instead of differential graded objects, and then you take a cosimplicial algebra, which is just the cosimplicial algebra of maps from K to Q. Okay. In that case, it's okay. So if K is finite, then you still get something. You still get an ISO. But in general, you only have again so product map going that way. So this map is an ISO if K and L are finite as simplicial sets, or dimension-wise finite. But in general, it's just a weak occurrence. So you still face problem with cosimplicial objects, okay? So something has to be done. So now I would like to explain how to use, so in any case, this model can be used to perform homotopy computations. I would like to recall how to do that, applications of models, so homotopy computations with models. And I would like to do also, I would like to recall the coherently generated model category structures we use for such computations. So we have three categories. You have the category of topological spaces, and I will put a 0 to say I will restrict myself to path-connected topological spaces. I'm also going to consider the category of simplicial sets, and again, path-connected simplicial sets. And I'm also going to consider the category of differential graded commutative cochain, commutative cochain differential graded algebras with units. Okay. So unitary. I will consider a connectedness assumption in that case too. Unitary. Commutative. Cochain graded. So maybe I need to make some conventions explicit at this point. So cochain graded means connected, and cochain graded means that the algebra means that the DG algebra is upper graded and vanishes in degree less than 0 and is reduced to K, to the ground ring, so Q, in degree 0. And so, unitary, and here this is just reduced to the units. Okay. And the differential is a derivation that raises degrees by 1. So I have so I have functors connecting these categories. So I have so from between topological spaces and simplicial sets. So in one direction I have the topological realization functor, and in the converse direction I have a singular complex functor. So where? So the topological realization is just a functor which takes a simplicial set to the topological space defined. You just take the union of the topological simplices indexed by the abstract simplices of Kn. You divide by the relations, which says that the co-phase operations here and co-degeneracy operations here correspond to phase and degeneracy operations in K. And the singular complex of the space X is just a set of maps, topological continuous maps from delta dot to X, and that way you get a simplicial set. Okay. So I have this functor APL, which is contravariant from the opposite of the category of simplicial sets to DG commutative HRS. So the first observation is that this functor has an adjoint. Observation. APL as a left adjoint G. So it goes from DG commutative HRS to simplicial sets. And it is defined by, so for DG commutative HRS A, dimension bullet, it's just a set of DG HRS morphisms from A to the DG algebra of piecewise inner forms on the simplices, delta bullet. So you take all morphisms of DG algebras from A to APL of delta dot. Okay. So for I should say for each dimension A. Each dimension. So this definition is obvious from the requirement that G is left adjoint to APL, and from the fact that the delta n in some sense generates the simplicial category. Okay. So you have this functor. So now the claim, so okay. So the claim that we can use that to do homotopic computations. So for that I need some structures.
So I can just two quick remarks. One is that this functor is denoted by angular brackets in Sullivan's paper.
Yeah.
And second, that for people who haven't seen it before, it's worth remarking that it's essentially a sort of derived functor of spectrum.
Mm. What do you mean?
The spectrum is Hom from algebra to,
okay, I see,
to Q.
To Q, yeah, okay. To
and
K.
so now we're
You
factoring.
replace K, you have the field where you take points of a spectrum by this DG. Yeah, that's right. Okay.
Not the spectrum as in
Yeah, exactly, topology. That's what
spectrum. The old fashioned. Spectrum as in
As in Newton.
Yeah.
Okay.
Yeah.
Okay. So to do homotopy friends, so in each case, so in each category, so what we like to do So let's say M. So this is one of these categories. Oops. So what do we have? We have a notion of weak occurrence. Okay. And we would like to, what we would like to, I'm using this notation for the class of weak occurrences. And we would like to, what we would like to do is to compute morphisms in the homotopy category. And the homotopy category is formally defined by inverting these weak occurrences. So it's very hard from this definition to do any computation. So what you are using is a covalently generated model structure. Okay. So this means the following. So we have these classes of distinguished morphisms. Called cofibrations, which I'm going to denote by that way, and fibrations, which are usually denoted by that way. And there is also a set I of things which are called the generating cofibrations. And a set J of generating acyclic cofibrations. So this is this is just a subset of a class of cofibrations. And here this is a subset of acyclic cofibrations mean maps which are cofibrations, which are both cofibrations and weak occurrences. And these maps, in some sense, characterize the fibrations. I mean, you have several axioms. Such that, so we have the following. Each diagram, so for each map P, for each morphism P, P is a fibration, respectively an acyclic fibration, if and only if each diagram of a form, so we have each diagram, so if and only if I should say P has the left lifting property with respect to the morphisms I in I, respectively J in J. So this means the following. So for each diagram, so the fill-in morphism exists. In any diagram of the following form. So A to B, I, X, E. So the fill-in morphism is this map, where I belongs to I, or respectively I belongs to J. and you have some additional axioms. And the point is that whenever you have such a structures, you can compute morphisms in this derived category from some object x to another y as homotopy classes of morphisms from R, a covariant resolution of x. So covariant resolution means that you replace x you have to replace x by a resolution which is an object which has the property that the initial map is a cofibration and this object is equivalent to x. So this is called the covariant resolution of x. And you have to replace y by a Farrant resolution. So Farrant resolution means that you replace y by an object S such that the terminal morphism is a fibration. And S. So here this is the homotopy, some kind of natural homotopy relation in M. Okay. So the idea is that this are some kind of analogs of the cell complexes of topology. So what I'm going to do is to make a table where I say what are the fibrations, what are the cofibrations, and what are the generating cofibrations and the generating acyclic cofibrations in each category. So to summarize these notions. So you have the category of topological spaces, the category of simple short sets, and the category of DG commutative algebras. So here are the weak equivalencies. So here the weak equivalencies are just the maps which induces an ISO in homotopy. So we call this map the pi-lower star isomorphism. So in simple short sets, the weak equivalencies are the maps of which realization is a weak equivalence in topological spaces. So these are the pi-lower star realization isomorphisms. So in DG commutative algebras, the weak equivalencies are the morphism which induces an ISO in cohomology. So let's say the H upper star isomorphism. So now I want to define the generating cofibrations. So generating cofibrations. So in the context of topological spaces, I can take the inclusion of a sphere, of an n-1 dimensional sphere, in the n-dimensional ball. In the case of simplicial sets, I take the boundary of the simplex, simplicial model of the n-simplex, the embedding of the boundary of the n-dimensional n-simplex into delta n. So here I have an analog of these objects here, these cells here, which are the maps So this is a symmetric algebra generated by some element B, which is supposed to be homogeneous of degree n, or n plus 1. So the free-graded algebra, free-graded commutative algebra on one generator of degree 1, and here, for the codomain, I take the free graded algebra with one generator in degree n plus 1, one generator of degree n, and I take the differential which maps this E to B. Okay. And I extend this map to the world algebra by using the derivation condition. Okay. So these are by definition the generating configurations of DG commutative algebras. So in J, generating acyclic configurations, you take what? So here you take these embeddings. So these maps are, so in each case you have to check that the maps are actually weak equivalencies. So in this case this is obvious because Dn is contractible. So here I'm taking something which is the corn, so the horn, sorry. I'm not going to say what it is. You just remove one phase in delta n. So just the subcomplex of delta n where you remove the k phase. Okay. In that case, what I take are maps from k to this DG algebra. The same differential. So I'm crucially using that, the ground ring is a field of characteristic 0 because this object has to be acyclic, has to be contractible. Okay. Q. Yeah. So. K equals Q. Okay, so this works for every characteristic 0 field. Okay. So when you have now the configurations. So in all cases, configurations are retracts of ith cell complexes. So this means that you get all configurations by repeated attachment of generating configurations. Okay. So in that case, so you cannot say more. So.
Something I'm confused. What values of n are permitted here?
Here. Sorry.
In the second line.
Yeah. So you can assume that n is larger or equal to 0.
No. First of all, 0 doesn't work in the rightmost column because that's no longer connected. And,
right.
And 1 doesn't work in the first column because the 0 sphere is not connected.
Okay.
Which, I mean, somehow what we're hitting here is one of the reasons why Coulin's paper is so long.
Yeah. Okay. Yeah, so here you have to, on this side, okay, let's forget about correctness. Okay.
And on the second line, the n greater than or equal to 1.
So here?
1. Not 0.
Not 0. Yeah, so here not 0, and then you can take 0. Okay.
You mustn't take 0 on the second line. It's not a trivial cofibration.
So this?
On the left,
okay,
pointing to D0 is not
D0, okay.
Oh, hang on, yes it is. It's an isomorphism.
Yeah, it's an iso, so.
Yeah,
okay, so let's forget
yeah.
that.
It's the second guy.
Yeah, the
It's
second guy.
suspicious.
Yes, maybe. so we move something to a point. Okay. That's what it is. Okay. So in all cases, the configurations are just made by a repeated attachment of such maps, okay, along the base. And so in that case, you cannot say more. In that case, you can check that relative state complexes are all injections, all injective maps are configurations. In that case, you can say more. You can identify the subject with quasi-free morphisms. I mean, morphism which has this form, E. So the algebra, if you forget about the differential, it's a tensor product of A with another algebra, where this basis is equipped with an ordering. So it's so each alpha is assigned an integer. Okay, and this D is a differential. So it's determined, so which is added to give the differential of this algebra, and it just assigns E alpha to the boundary here, which you have put in lower terms. Okay, it's the cell attachment process. So it's D alpha has to belong to A tensor, the symmetric algebra generated by the elements beta, which are lower than alpha with respect to a fixed filtration. With respect to the filtration. So okay, you don't have to forget this condition. And now we have to determine the fibrations. So these are characterized by the left lifting property with respect to J. So here we get the Serre fibrations. And here we get the Can fibrations. And here we get all surjective maps. So the definition of a model category structure works pretty well if you don't deal with connectedness assumptions. But if you try to compute with the Sullivan model, then you really need this connectedness assumption for the algebra, actually. Okay. So maybe the connectedness assumption is not it's just necessary in the third part of this talk. Okay. So we have that. So we can do homotopy computation. So here is the classical thing. To do homotopy computation, you just replace any space by a recurrent CW complex. So that's the idea. Okay, so every space is fibrant. And here you have, so every space, every simplicial set is cofibrant. But what you have to do is, in order to compute homotopy classes of maps, morphism in the homotopy category properly, is to replace the simplicial sets by a fibrant resolution. So this is the main complicated point. Okay. So I'm glad to give two statements. So the main theorems. So that the functors, so we have these functors. So these functors form a Coulomb pair. Pair. Or I will say this is a proposition. Okay. So these functors form a Coulomb pair, and as well as the functor, the Sullivan functor, the functor G, oops, Oop. The functor APL. Okay. So for a Coulomb pair, this means that these functors have well-defined derived functors. Which induce an adjunction at the level of homotopy categories. At the homotopy category level. then you have more. And so in this case, this Cullen pair is a Cullen equivalence. This one is actually a Cullen equivalence. So this means that these functors induce adjoint equivalences of categories at the level of homotopy categories. So I think this statement is a result of John Milner, probably, before the invention of model categories. Before the, okay. And so in that case, you don't get a Cullen equivalent, but you can look at the. So if you start with a space, go to differential rate commutative algebras, and go back to spaces, so we can look at the result of this process. So I take the derived functor of G, APL of X, okay. So this is a theorem. So derived functor, so I start with a simplicial set K, I take the Sullivan-Durham functor, and I take the derived functor of G, okay. So this is G applied to a cofragment resolution of this object. For some cofragment resolution R of A, K. And the claim is that this object is a rationalization of K. Of K, at least if K is nilpotent, at least if K is connected nilpotent in the cohomology of K is degree-wise finite. Okay, so I just say it's finitely generated. It's just degree-wise finite. So if you apply this machine, so from simplicial set, go to differential rate commutative algebras and go back, then you get a rationalization of the space. Okay. So I will not be able to address the computations of homotopy automorphism, but I can explain in a couple of minutes the example. So if I start, this example, I take the classifying space of a pure braid group, which is the space of configuration of points in the Euclidean plane, CR. Okay? So it's a set of points C, so let Ci is different from Ck, or I is different from J. So I claim that in this case you just retrieve so it's basic, so it's a consequence of this statement, you just retrieve the classifying space of a Maltsev completion. So this is the pure braid group. Okay. you can actually get another representation of this object. So you follow the following approach. So you take the cohomology. So it has been said that the cohomology of the configuration space is the symmetric algebra generated by forms omega ij. So for ij runs over pairs. So it's a free-graded algebra generated by forms of degree 1, and you divide by the ideal generated by the Arnold relation.
Also, I'm confused on the first place. So you take the nerve of the pure grid group, you realize, and then it's homotopy equivalent to the configuration space.
Yeah, exactly.
So
Yeah.
it's homotopy.
It's all okay. Sure. So the cohomology of this space is the free-graded algebra generated by these forms. And so the Arnold relations reads omega ij, omega jk, plus omega jk, omega ki, plus omega ki, omega ij is 0. And if you work with a complex theorem chain DJ algebras, then omega ij is just given by the class of the logarithm of zi minus zj. Okay. So it's a class, the Durham DJ algebra, the DJ algebra of Durham forms on this configuration space with coefficients in C. Okay. So what you have probably learned, so this algebra actually is cosule. So you see it's a quadratic algebra in the sense that Bruno explained. It's actually cosule. Okay. So this A is cosule. And the dual straight is the enveloping algebra of some Lie algebra, PR. So this PR is the Lie algebra generated by elements denoted by Tij. So this is again for every pair ij. So you divide by the infinitesimal Bride relations. So the infinitesimal Bride relations reads Tij tkl is 0 if for every quadruple of distinct integers, and Tij tik plus tkj is 0 for every triple I different from j different from k. Okay. So it's again it's a quadratic Lie algebra. And cosule means that you have a cosule directive equivalence which goes from the Chevalley-Ellenberg cochain complex of this Lie algebra to this credit commutative algebra. And you can actually see that by using these generators, that this equivalence lands in the cochain DJ algebra of Durham forms. So this implies that it's the map which sends it's a it's a quasi-free algebra over the desuspension of the dual of R. Okay. You have the Durham differential. So this map sends the dual of Tij to omega ij, so to d log. And it vanishes on the monomials of higher weight. Okay? So this means that this DJ algebra represents a covariant resolution of this object. Okay? sequence. So you can compute you can use this object to compute the image of this DG algebra under the derived functor of G. And what you get is that LG of A, F, C, R. So it's the image of this object under this functor. And what you get actually, and you can easily determine all the algebras morphism from this side to this side. And what you get are the elements satisfying the Maurer-Cartan equation in PR, which completely tensor product with this commutative algebras. Okay. And you can also identify this object, so it's a purely formal identification. Okay.
Is DR, no, you confuse this ADR. Here you have manifolds, so it's the different forms.
Yeah. Ah, okay.
Yeah.
Yeah. Okay. It's also true with PL. It's not so clear at this stage.
Yeah.
Okay. So for now, I've just proved that this object is formal over the complex numbers. And you need more in order to prove that it is formal over the rationals. Okay? And what you get in that case, so it's over C. So you get this is the definition. This is just a formal identity. You determine all the algebra morphism from this guy to this guy, and you can easily check that they correspond to elements in this Lie algebra, satisfying the Maurer-Cartan equation. And you can also check that this object is equivalent to the classifying space of a set of group-like elements in the enveloping algebra of PR with the completions. So this is for group-like elements. Okay. So you can use that to do computation in this space. Okay. So now, okay. So probably not address the applications of minimal models to the determination of homotopy automorphism in spaces. So we mark a break at this point. And then, so the goal of the next talk is to explain that this object is a model in the operatic sense, and to also to give an operatic counterpart, an operatic upgrading of this DG algebra of piecewise linear forms. Okay.
Not that one. You said that's not Durand.
Yeah, Durand or PL, it works same. Okay. Maybe PL. Okay. You know, so I can use, yeah. Yeah, what I need is, this, I'm just using this object. Okay. So I mark a break and I resume at 3:45 or?
Yeah, 3:45.
3:45, okay.